So you probably already heard about WebAssembly today. It's a new low-level bytecode for the web. It's a stack-based virtual machine, and it produces these .wasm files. And it's used for calculations, computational tasks, importing low-level libraries, multimedia processing, game development, and a lot of Bitcoin mining. So, good thing though, it integrates well with the web developer workflow. There's been a survey done this year by usages of WebAssembly on the, I think the top Alexa websites, and the result was that it's used for mining a lot, but also for good things like libraries, gaming, and other kind of custom code. Meanwhile, this morning, nobody mentioned this, I think, in their slides, but WebAssembly is now officially a web standard. So it's a huge, yes, yeah, claps for all the developers, contributors, browser vendors. We made it. Now it's the 4th language that's on the web. It allows to run code in the web browser. And yeah, I tweeted just 9 a.m. It was just like, yes, you can go read the details. And even though we just standardized it, it's already here and it's ready for you to use. There's an easy way to integrate WebAssembly in your applications. For instance, some libraries like Pika, the high-quality image resizer, has this amazing way of integrating WebAssembly. All you have to do is to pass the WASM string into the options, and Pika is ready to optimize and resize your images in your apps with WebAssembly. So preparing for this talk, I took all the images from the dotJS website, 130 of them, mostly speaker faces, and resized them with JS. It took me over 2 seconds with Pika. Then I forced the WebAssembly mode on it, and it took less than a second to process all those images. So very easy to use, kind of you can get on that. But we want to go and optimize our own applications and our projects. And sometimes you get this sense where maybe power users or like if somebody's really heavily using your application, it starts to slow down. And maybe it's processing a lot of data, processing images, video, and things like that. So we have this problem that it's a bit slow on the computation side. And here's a quick example of that. We have some application that computes things. Then there's this gear icon that starts spinning, and then we get the output. And I want to take this example, kind of my example here, to hash strings. And what I'm doing here is I'm using this 2x hash algorithm to hash a string 100,000 times. And there's an implementation of it on NPM. You can download it, check it out. And what I want to do is I want to speed this up, because right now it takes around over 2 seconds, yeah, almost 3 seconds there, sometimes even slower, to run this hashing operation. And in your heads, I just want you to kind of think about your application when you see this slide. What's the kind of where's my computing logic happening? What can I substitute here that's taking time? I think in Charlie's example this morning, she was doing the audio processing. So we can switch this gear and put the audio processing into a WebAssembly module. So then we need to decide how can we. What can we use to write this WebAssembly module in? And in this slide, that's my order of preference here right now, which is first I'm going to go to Rust if it can do it. If not, then I will explore the assembly script, see if that can do it, and maybe the C is the other solution. And for you can just visit the webassembly.studio today. It will give you this pop-up that will show you kind of give you choices of how these WASM modules look like when you use these different technologies. So here's our goal. We're going to replace this gear icon with a WASM module. And we've seen Webpack mentioned at this conference a lot. So Webpack is kind of the way to, here we go. Let's try this again. So we have Webpack that can do this for us. There's an amazing module called WASMPack that will create a Rust crate for you and will let you optimize your application. So when we use WASMPack, it creates a Rust crate for us, all ready to be used, and we can import the 2x hash version, the Rust version of this algorithm into our crate. And then a simple function to, same as JavaScript, we have an input string, and we run the hasher on the string, and we output it as hex format. In this case, you'll be rewriting your heavy computational logic here in Rust. And finally, in Webpack, all we have to do with WasmPack, we include a plugin the WasmPack plugin over there, which will build our Rust code for us. And it's as easy as just doing a new WasmPack plugin and pointing it at the direction of our Rust code. And what you'll see, and then we can import the bundle that it produces, and then we can run the module functions that we wrote in Rust. So we have 2x hash there on input, and we run it hundred thousands of times. What I'm doing here is another kind of approach that I take when I work with these things. I try to measure all this. You saw in my slide there, like I wanted to measure how long how long Pika takes to resize images, and how long it takes right now to do my computational logic. And so I do performance.now on that. And my Webpack workflow here doesn't change. I still do npm start. This time it compiles my Rust code as well. So no additional changes to my build scripts. It does that automatically. And now I can activate my WebAssembly module. And now it takes 200 milliseconds to perform the same operation. So then I can spin on the gear. It's so fast I had to tweak it so it slows down a bit so you can see the animation. The other approach here, we want to make sure we use web workers with WebAssembly. And I've seen examples of this right now, creating abstractions like create WASM worker, pass the source WASM module, and then work with it. And this sort of looks like this, where we have the web worker isolation here. And the web worker runs WebAssembly and performs the computation there. And it will look very similar. Now we have a worker.js file, same code. With web workers, we have to use messaging. So I have to post message my result of my hashing to the original application. And this is just the simplest way to kind of trigger that. And when the message arrives, I run the computational logic. In my application, I can initialize a new worker with the worker.js file and send it some messages and say, okay, here's the string I want to hash. And in this case, again, I'm measuring the performance and to see if adding web workers slows down my speed, the 200 milliseconds that I gained with WebAssembly. And there's some cool spinning classes for the CSS to spin. If we look at Webpack, still same thing. We just tweak our configuration a bit. We now have an app configuration file. We're still reusing the same plugin, but now we have two configurations. We have the original application, and then we have this worker. Webpack targets set the target as web worker, and we reuse the same plugin, and nothing changes there. We can take a look in Firefox. I have two tabs open, one with web worker, one without, and same speed, around 200 milliseconds to measure that. And in Firefox DevTools, we can take a look at the WASM module right there, loaded as part of the web worker. So why would we want to use web workers? If we compare, we could compare the web worker versus not a web worker scenario. So I'm going to do a million hashing application iterations now in both cases, in my the original example and the web worker example. And we can run it. So the first one is going to be the old example. And I activate WebAssembly, compute it, and it takes a while. And I try to right-click in the browser, and my browser is just locked up because it's not inside a web worker. All this computation is done on the main thread. In my web worker example, I can right-click. The browser is accessible. Still, the average is for a million operations now. We're at around 2 seconds. Now, I also want to talk a bit about the future of WebAssembly and where this is all going. There's a lot of Sven mentioned a lot of proposals and support in there. Another initiative is what's called the Bytecode Alliance, and it was just announced last month, so it's really fresh. And the Bytecode Alliance is the open source community. It is dedicated to create new secure software foundations through WebAssembly. And they have several initiatives, and you can read about more on the URL there, but the ones I'm excited about are the WebAssembly system interfaces. And this will allow us to run WebAssembly outside, sort of beyond the web browser. And so this will allow us to, for already fast languages like Rust and C++, it can introduce better security models for those languages. And runtimes like Python and Node.js and maybe Deno, we can use the WebAssembly speed as well as the security improvements. And it would look something like this on my slide there. The future of this is we start with the Rust crate that does our, for example, 2x hash computation. Later on, a Rust program can import that code as a Rust crate, but it can also import that a WebAssembly module that we run as part of our Rust program. And then we have kind of the top there is like Firefox loads WebAssembly. You've seen an example of that already. But for example, Python can load the same WebAssembly module and also load one from assembly script. And the Python program outputs to terminal, but also it exports to a Node.js server. And this week there was a post about .NET being able to use and load these modules as well. So you can see how flexible the future can be here. Another, besides kind of loading these crates, these modules, the WebAssembly modules in different ways, we can also, the Bytecode Alliance is working on a new kind of nanoprocess security model. And I think that was kind of, I think the Deno talk, Bert mentioned this, where they have permissions for networking and kind of sandboxing things. So the nanoprocess security model is basically, in a single slide, this is what it would look like. We have a Rust crate, and it could be the 2x hash that you saw an example of. Exported as a WebAssembly module. However, it has its own memory sandbox, and for instance, it can have network access. And then it can be imported in a Python program that also provides a WebAssembly module, but this time, that WebAssembly module only has file system access. And with JS, we can also like sandbox memory. And finally, import that all into the Node.js process. And for instance, if I have a Node.js application and my 2x hash crate updates, and I'm just kind of doing cargo update or updating my dependencies, I don't know if like there's going to be something malicious in there or not. In this case, I can be confident that if I give the 2x hash a network access, it will kind of have it, but it won't have file system access. So, and same with the memory. It will not corrupt my memory because it's running in its own sandbox memory case. A quick demo of the WebAssembly system interfaces. Just to see this in action. We have the same code that I showed in the beginning there, the 2x hash. Nothing changes here as far, it's the same thing. We just build it a bit differently. In Webpack, to make this work in my front-end application, I change it to use the WASM interfaces types loader. At some point, probably in Webpack, this will go away and it will just work. And my application works the same way. So I go back and like in this case, it's still fast to compute this. What I can do now is I've built this module, and for instance, for maybe your production work, you want to reuse the computation that you wrote in other ways. You want, for example, you have a Python notebook that needs to import the same computation and do some metrics on your code. So, or maybe another Rust program. In a Rust program, we can just load the file to hash.wasm. There we go. And we can build and run the application, and it provides the hash for us in 0.07 seconds. In a Python program, same thing. Just import to hash. To hash is just the WASM file that I've built, just a similar way I showed you. And we can compute another thing. So now we can run this WebAssembly module in the Python context. And we just do the old Python run.py. Same thing. Produces a hash. Now we have a different string, but very flexible for us to kind of reuse these modules. Finally, my favorite example is running this in Node.js. We import compute from toHash.wasm and compute another string. You can just console log it. And now we can kind of move this two-hashing logic that we used in our Webpack front-end application onto the back-end. To use this right now, you need Node version 12 or Node version 13 with some experimental flags. And we run the program the same way, and it will provide us the same output there. Boom, another hash. So you can see the flexibility of kind of reusing this code that you've optimized and now have as part of your project. So just to conclude here, use WebAssembly wisely. You saw I was benchmarking kind of almost everything, adding workers to my front-end application, measuring it on different inputs, and use web workers. One important thing to highlight here is that the reason I'm measuring all this is because WebAssembly might not always be kind of a solution for this. So if you have a large input, like maybe you have a huge book that you need to process, and you take this and your front-end application, and you try to process it in the WebAssembly module, all that input has to travel to the WebAssembly module and allocate memory and things like that. So it's like, it could not be the solution. That's the reason why I measure it. Keep an eye on your output size. So there are several optimizations you can do. There's some Webpack plugins that let you measure like your bundle size, and keep an eye on the size of the WASM modules, because you can tweak a single flag in the kind of the module building step, and it will optimize your size of the output. So it's a good one. And research different WASM runtimes. So once you actually write your first WASM crate or WASM module, try to run it in different environments. Maybe run node.js, in which you can later use for testing, or in Python and things like that. And try to go beyond the web browser. It's a very exciting time right now to kind of reuse this format and follow the news there.